Wav2vec, semi and unsupervised speech recognition, quantize phonemes from audio, transform and GAN the text. So hi, welcome back, and yeah, we would like to subscribe. You can subscribe on YouTube. You can subscribe by mail as well on my blog down here at the end, and as well you can share and especially let me know. I'm getting into machine learning, so I'm getting better every day, and let me know if I made any mistakes. Alright, so there are many languages in the world, and we want to convert audio to text for all of them. There are around 7,000 of the languages actually spoken today. Although I'm not so sure about this number because there are around 200 sovereign states and 150 language groups, so I expect that lots of these languages are actually very similar. And the issue is that we lack labeled data for most of the languages. And as well, humans learn without labels, right? So humans have this intuitive thinking that can learn intuitively, this sort of system 1, and they also have this system 2, this sort of more abstract, more discrete thinking machine. So maybe we should do something with discreteness. Alright, Wav2vec 2 is one of the super interesting papers that look into this area. It's from Facebook AI. It's a framework for self-supervised learning of facial representations. It was released on Archive on 27th of October 2020. What they do there approximately is that they pre-train on large amount of unlabeled data, and then they fine-tune on 10 times or 100 times less data. And they are able to achieve state-of-the-art on low resource setting in terms of word error rate. And in this low resource setting, they are significantly and quite a lot better than the competition. By the way, the word error rate is actually word level, word count normalized edit distance. So if you know what the edit distance is, that's easy. Edit distance is just how many edits do I need to do to change from this to that. So this one is on the word level, how many words I need to change, insert, delete, swap, and I also normalize. So state of the art on low resource settings. In high resource settings, it's only state of the art on noisy data and by a small margin. And it is close to SOTA on clean data, but not quite state of the art. It uses quantization as an inductive bias, sort of looking for phonemes in the spoken text, right? So what is a phoneme? So phoneme is a unit of sound in spoken language. For example, in international pronunciation language, we can there is a word sin and sing, and they both are very similar, 3 characters in the pronunciation language, but they differ in the last one, right? In English, we have around 40 phonemes. And what is quantization? Well, quantization takes a vector and replaces it with a vector from a finite set. Usually, we use cosine similarity. In high dimension, in lower dimensions, you usually use Euclidean distance. Forward, and so during forward pass, that's what I described, we just pick single vector from the codebook. In the backward pass, we use actually softmax over all the entire codebook, and we make it differentiable in this way. As well, there's this product quantization where we can concatenate several quantizations and then apply linear transformation. and the jointly is called product quantization. So what it gives you is that in Wav2vec, how quantization works there. Well, the codebook is a product of two codebooks of 320, which gives us around 100,000 discrete vectors. And the codewords dimension is around 256, which is kind of both subcode books have 128, and now you could ask, okay, so what's about it? Well, what's interesting here that the dimension is very similar to Wav2vec, and the number of code words, the number of discrete vectors is very similar to the Wav2vec. 100,000, something like that. So does this actually work, and why should it work? So well, what we are doing in that model is that we are taking some representations and mapping into some discrete codebook. Why would we do that? Well, as I just mentioned, sound of languages is composed of the discrete pieces, discrete units, and those are the phonemes. And in English, they actually did this current analysis, and they found out that the most of the discrete presentations actually occur in presence of one single phoneme most of the time, right? So if we will look here on the y-axis, we have a phonemes. On the x-axis, we have a probability distribution over the code words. And you can see that each code word, mostly seem to be specialized in single phoneme. Of course, there is some other occurrences here and here and here, right, around, but most of them seem to be, most of the weight seem to be on this line over here, right? All right, so how exactly this architecture looks like? Well, so it takes in the raw audio, right? We are doing speech recognition. It outputs sequence. How does it work in between? So take raw waveform. We do convolution on top of that, with some overlapping kernel, and then we take the output and we quantize it, and we do this only from the training time. It's only important for training, and we also follow the other part of the fork, and then we pass that to a transformer. And transformer, there are around. By the way, the transformer has 12 blocks. The convolution layer has seven layers. Okay, so the transformer contextualizes this representation. All right, so what we do with them, what do we do with the quantizations? Well, the quantized vectors are then participating in a contrastive loss, where the transformer tries to recover masked inputs and sort of masked inputs, what quantizations correspond to them. So it doesn't directly predict the masked input itself, it predicts the corresponding quantization. Right. As well, there may be one more question, right? So this is pre-training, right? But we want to convert to text. So how do we go from this sequence to the actual text or to the phonemes themselves? Well, just on top of this, we can just apply sequence-wise linear classification. That's what they did. All right, and another question may be, all right, so you do these quantizations, are they actually useful? Why we do them? And this is possible without them. Actually, they did ablations, and this seems to work. This seems to help. Is that you sort of force you introduce this inductive bias to force the network to look for some look for these discrete representations. Right, and fine-tuning, what I haven't mentioned is that once we have the sequence, once we have the output, we would like to fine-tune and predict characters or predict the phonemes. For that, we use CTC loss, or called connectionist temporal classification, CTC loss. So that takes unsegmented time series and target sequence, and then calculates loss. How does it do that? Well, it calculates sum of all possible alignments between input and target, and it does it in a differentiable way. How exactly does it work? Here's a link to the paper. Essentially, the problem is that, as you might imagine, we have these pieces of text as inputs from the convolutional neural network around 30 milliseconds, and what we get on the output, as you would expect, we could get some repetitions, right? Because this 20 milliseconds contained this character, but the next one again, because the person was speaking very slowly. So what we do, instead we want to throw away the duplications in the characters, and even the duplications in the silence pieces. So we have this mapping which removes all the duplications, but suddenly for one label there are many possible inputs. So how do we deal with that? Well, this is what the loss counts on, right? But you can imagine that it may be expensive to calculate this, because for each output we have probabilities of which character there may be occurring. So how do we go from calculating all possible labelings and their probabilities to actually the sum? How can we sum this somehow fastly? Yes, you can do that using dynamic programming. You essentially calculate something in forward and calculate something in backward, and it's fast. How is Wav2vec actually different from the previous versions? So the previous version is this VQ Wav2vec, and there instead they trained the quantizations separately. So here in Wav2vec 2 we learn quantizations and the network together during pre-training, and then we only fine-tune the last layer. So it's sort of like the pre-training is single step, whereas it was two-step. What kind of losses we use? As I mentioned, we do this contrastive loss. So the transformer output tries to predict codebook corresponding to the masked input. It uses similarity because we are in high dimensions. Distractors are and distractors. It tries to select the correct quantizations from the distractors, and those are just corresponding to other masked steps in the sequence. And there's a question: why does it not collapse to a single vector? Well, there's diversity loss, which encourages even use of the codebook. The entropy of the average softmax for the batch over the codebook is used as a part of the loss. And this paper does improve on the previous version of the paper. It has a word error rate of about 33% better, lower. All right, so that sounds nice and dandy, but can we do even better than this? Well, in 2021, there is this new version of this paper. It's called Unsupervised Speech Recognition. and this one trains without any labels at all. It is inspired by other adversarial approaches, and it sets state of the art on the unsupervised setting. It is not competitive with current supervised models, only perhaps with those models from 2018. And how does this crazy idea actually work, right? So you take unlabeled speech idea, you pass it through Wav2vec 2, you get the speech representations from there, then you cluster nearby outputs and segment them, build a new sequence from those that were clustered together, that were nearby and were clustered together. You pass these, you average those, you pass that to a generator, which is a convolutional, single layer convolutional network. Generator generates some phoneme sequence, and then that is passed to a discriminator, and discriminator has no labels. It only tries to recognize what is real and what is fake. And the goal of the training is to make sure that the discriminator is no longer able to recognize what is coming from the generator, which is based on the unlabeled speech, and what is coming from unlabeled text that is phonemized, that is converted using some simple algorithm into phonemes. Right, just quickly, other details. The discriminator is also a convolutional neural net. Right, so this is very cool architecture. I haven't read too much about that, but it sounds very cool. So, okay, that's all I have. You can subscribe and you can let me know if you think I left out some details, what I should add, and so on. Okay, thanks, and see you next time.